This video covers topic 15.1 over transformations of quadratic functions. So up at the top, we're asked to recall the most basic linear function, which is the linear parent function y equals x. The quadratic parent function is the function y equals x squared. So problem 1 has asked us to take this and make a table and graph the quadratic parent function y equals x squared. The table's already been done for us and the graph has been done for us. We are just going to identify some missing pieces. My vertex is the lowest or the highest point, the point where my graph changes directions. So my vertex is at the point 0, 0. My axis of symmetry is x equals the x from my vertex, because that is the vertical line that goes straight up and straight down. My intercepts cross at 0, 0, and for the quadratic parent function only, your x-intercepts and your y-intercepts are in the same place. Your domain for all quadratics is all reals, and then your range, we start at 0, we know it's 0 because that comes from the vertex, and then we go up, so my range is getting greater than. So problem 2, you don't have to turn the page, we just have a new graph. Problem 2 asks, how does the graph of x squared change? So looking at this graph, we have x squared in black, 2x squared in blue, and 5x squared in green. So as the numbers in front, which we call our a values, as our a values are getting bigger, our graph is getting skinnier or narrow. So if you have like a doorway that's really narrow, it's really skinny. So if you see the word narrow, think skinny. These graphs are being stretched by whatever number is in front. So instead of a 1, it's twice as tall, or it's 5 times as tall. For problem 3, we have x squared, 1/2 x squared, and 1/5 x squared. So this is my original x squared, this is 1/2, and this is 1/5. So as the number in front of x gets smaller, the graph gets wider or compressed. So think about if you were like a giant and you were pushing on this x squared graph, it has to go somewhere so it pushes out and it's half as tall. Or you really push it and it's now 1/5 as tall, but it's really, really wide. For problem 4, our x squared is on top and our negative x squared is on the bottom. So this one changes by being reflected across the x-axis. So putting a negative in front flips your graph to look like a hill instead of it's a max instead of a min. And then problem 5, we have x squared in black. X squared plus 5 is in blue, so the plus 5 scoots up 5. And then the minus 5 in the back goes down 5. So now on page 2, we're going to talk about what happens. So my a value is what's in front of x squared. K is what follows. So we're looking at this when they reference the letters a and k. So if a is greater than 1, if we have a number bigger than 1 in front of x, the graph stretches vertically. And this is the same thing as being narrow. And you will see these words interchangeably, so you need to know them. So when a is between 0 and 1, like a fraction, the graph compresses vertically. And then when a is less than 1, so you might want to write this means negative. When a is negative, the graph reflects. So all of these, stretch, compress, or reflect, all deal with the number in front. Now k is the number in the back. So if k is positive, the graph shifts up. And if k is negative, the graph shifts down. So A in front before the x squared stretches, compresses, or reflects. K in the back, if it's a plus, it goes up, and if it's a minus, it goes down. So 6, 7, 8, and 9, we are matching, and this is what a lot of your assignment looks like. So I start with the ones that go up or down. So the only one of these that goes +2, which means up 2, is D. I notice D looks like a mountain, which fits because this means I'm going to flip it. So 7 would be graph D. This one goes up 2, my vertex goes up 2, and then it reflects, so it goes down. My range for graph D, we start at 2 and we go down from there, so it is a less than sign because you're going down. The next one I would look at is the -2 because that one means I'm going to go down 2. The only vertex that goes down 2 is graph B. And then for my range, I start at -2 and go up, so I'm getting greater than -2. This leaves me with A and C, and I'm looking at 2x squared and 1/2 x squared. Remember that a big number stretches but makes it narrow. So between A and C, C is more narrow, so C would have a 2 in front of it. The bigger the number, the skinnier the graph. And then my range starts at 0 and goes up, so it's getting greater than. So then obviously 9 is A. A is fatter, so it's at a 1/2. I start at 0. I also go up, so this one is also a greater than. Problem 10, we have a graph f of x down here and g of x up here. F of x is a graph x squared minus 7. What is the equation for g of x? So one thing that we have to watch out for is sometimes if we're not being careful or if we're really trying to make things go our way, we think that these graphs look different than they really are. So here's how you can check to see if one is stretched or compressed or not stretched or compressed. I can start at my vertex, and if I go out 1, up 1, out 1, up 1, I have 3 points to base off of. So if I try the same thing on G, I'm at my vertex, out 1, up 1, out 1, up 1. If these match, and we know there was no stretch or compress on F, then there is no stretch or compress on G. Which means the only thing that's happening with G is that it moved up from the vertex, it goes up 2. So every time you put a number behind the x squared, it is in reference to the vertex. Now, how does f of x compare to g of x? F of x is below because it's underneath, and it is 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is 9 units below the graph of g of x. Problem 11 says that if f of x equals x squared plus 3 is shifted down 6 units, what would be the new equation for the translated function? We know that going down means put a negative in front of it, so we are subtracting 6 from where we're starting because we're going down 6 from the original graph. There is no change with the x squared because it doesn't say reflect, it doesn't say stretch, it doesn't say compress. And 3 minus 6 is -3, so that would be my new equation that is shifted down 6 units from the original function, not from the vertex. Problem 12 asks how does g of x compare with h of x? And I'm showing you what I would do is plug this into a calculator. Now we've already done it for you, but I would put g of x in y1 and h of x in y2. Remember when you press graph, the first one that comes up is the first thing you put in, and the second graph that comes up is the second thing that you put in. So when we're looking at these, g of x pops up first, h of x pops up second. So we can see h of x is below g of x. They are asking us the graph of g of x, so we need to flip our wording. H of x is below, meaning g of x is above. The only one that says above is A. G of x is up here on top, so it's not below, it's not to the right, and it's not to the left because they both line up. And then 13, they want us to start with a parent function and then vertically compress it. So to compress it, we need a small fraction. Keep in mind something like 11 over 2 is a fraction, but it will not compress because 11 over 2 is really a big number. So something like 1/2 x squared would be a small number. 1/2, if you eat half a pie, that's not a whole pie. So something smaller than 1. To vertically stretch it, we need a big number, so something like 5x squared. To translate it up, we need to add a number to the end, so something like +3 at the end. And to translate it down, we would need to subtract something from the end, like x squared minus 4. So just a quick tip on your assignment. If you are struggling with these, the first thing I would do is get my notes page out and make sure I have this page, the second page, out next to me as I am looking at these graphs. However, something we didn't hit on a ton, but you can use, if you're not sure the difference between like these two problems, you can plug this into y equals and see which of these graphs matches my equation. So if you're not sure, put an equation into y equals and compare the graph in your calculator with these graphs. Notice this graph only is a 5 by 5 and your calculator will do a 5 by 10, so they won't look exactly the same. But it will give you a good indication of the general idea of what you should be looking for. If it opens up, if it opens down, if it scoots up, if it scoots down, if it's skinny, if it's fat, etc.